So once again, welcome back to the last session of this FDP, where the focus is on life cycle assessment. Now, the whole course has been targeting on renewable energy sources, and that is where your future lies. But how do you determine what is sustainable and what is not? It might sometime be possible that the sources which are sort of fossil based have much lesser emissions as compared to renewable energy sources. It's not always the other way around. Now, renewable energy sources, the first thing that goes in mind, have less amount of CO2, but that might not be always correct. And how do we determine what is good for us and what is bad for us? And that's why you would see like nowadays the trend is more on the sustainable sources of energy rather than renewable sources of energy. Now, sustainable is anything that would go a long way, that would take care of both if the source of energy is finite or not, as well as if it's causing emission or not. And this sustainability, how to determine that, is something we'll get a glimpse in today's class, where the focus would be life cycle assessment. So without waiting much, let us start. I would request everyone to mute their mics. I can hear that some of the people are in the unmute stage. So that would be beneficial to all of us. So I request everyone to mute themselves in case they're not speaking. Which would be life cycle assessment. We'll go through its basics and some of its application in the energy system, and specifically renewable energy systems. To start, what do I mean by life cycle assessment? So as the name suggests, it has a life cycle in it, which means throughout the life, which means from the extraction of raw materials and disposable. And the assessment, we are assessing how much emissions it is causing. It's not only just CO2 as might be intuitive, it has much more to it. So if I go by the dictionary definition of life cycle assessment, it is something that you can see on the screen. Compilation and evaluation of the inputs, outputs, and the potential environmental impacts. So you might, it's the potential environment impacts that I am saying here of a product system throughout its life cycle. And you see there's an asterisk here, which means how do I define life cycle is also defined, and that is guided by the guidelines. And one of the sources is the ISO, which is an international standard, and we have particular guidelines into it. So just in brief, what does an LCA do? It will divide the process into different stages as well as phases. We break down a process to get a better understanding of the product, how it is formed, what are the different raw materials used, what are the different emissions. We collect data on the different inputs and outputs of the system. Now, there would be different inputs that are going in through the life cycle of the product, and there would be different outputs. There would be different emissions and different, like there would be emissions when you extract the raw material. There would be emissions when you use electricity. In the term, you're taking grid electricity, and that electricity is being formed by burning of fossil fuel. So even that electricity is associated. So we quantify all of these, and then we associate the environmental and the resource impacts. What would be potential using these inputs? So this is what we aim at. You already have a preliminary introduction to LCA in the class on Wednesday, where we were studying the case of ammonia production from biomass. And you could see that we estimated the life cycle assessment for that process and how the results look like. Today, again, we will take a similar example towards the end of the presentation, but I believe like you have some visualization in your mind what the LCA process looks like. Now, a brief about the history, like how did this come into being? So the process was developed somewhere in the late 60s and the early 70s. And it started with energy analysis. People thought of like like the core, like the things like energy and exergy were becoming famous at that time. And people thought like it makes sense that how much energy is being consumed by a process, and there would be huge savings attached with that. And this is what was observed as well. It later on turned or like got linked with resource analysis as well, because for energy you need resources. Different resources will give you different forms of energy. Finally, towards the 1990s, we have the Kyoto Protocol, and the impacts of CO2 were becoming even more severe. So people thought of including that as well, greenhouse gases, which was basically CO2 and the equivalent gases. And finally, by the time we came to 2000s, it had much more to it. It had the concept of energy, it had the concept of greenhouse gases, and many other emissions. And the total analysis, which contributed the energy, the resources, as well as different emissions, came to be known as life cycle assessment. So it was only after 2005 2010 that the use became more prominent. An example could be like there were certain reports like the OECD report. OECD means like Organization of Economically Developed Countries. And they come up with a report which is called biofuels. Is the curse worse than the disease? So you might be like interested in reading a report like this. So what this report brought about was like there was a boom in the production of biodiesel in the US at that time. So there was a lot of like corn fields, or like basically corn that was used for biodiesel production. And it came to light that this particular process in its water consumption as well as like the transportation was in fact leading to more emissions than would be caused by any fossil fuel equivalent. So that's why it's called, is the cure worse than the disease? And people became thinking like in the right direction. Not all renewable sources could be relied on blindly. We need to do this analysis. And that is when the process became even more prominent. Okay, so let's come. What are the commonly used LCA matrices? By matrices, I mean like what are they trying to determine? So as we started, it was the energy. Then claim the global warming or the climate change or the CO2 emissions. So like nowadays, people want the term climate change to be used much more often than global warming, because global warming has a sort of negative intonation associated with it. But when you say about climate change, it's just a change. It's a neutral term. So you can't blame anyone. So that's why like it's just the language that people are been, like using, and they often want to use climate change instead of global warming. Then you have ozone depletion. We have ozone layers in the stratosphere, which leads to the coming of the ultraviolet lights, and that causes problems like cancer. We have the water footprint. Specifically in a country like India, the water footprint makes a much more sense. We just can't rely on processes which use a lot of water, because we don't have enough water to supply to our people. And in a situation like this, if you're using water and a lot of water for the production of energy, it might not make sense. Then human toxicity, like certain things like nuclear power reactors would lead to nuclear radiations, which could lead to many toxic effects. How do we take care of those? That might not be applicable everywhere, but in the vicinity it does. And the effects could be somewhere more severe than the CO2. So we need to take into account. And last but not the least, land use. Again, like it has much more consideration in our country. We have limited amount of land, and most of it is being used for productive purposes, either agriculture or industry. And we have a huge population. So if I am using a lot of area of land for maybe installing solar panels or wind fields or even growing biomass for energy, does that make sense? Because that land could have been used to produce crops which could be used to feed people. And of if I'm using that land after clearing a forest, maybe for solar, it might be a net addition of CO2, because those trees were already sequestering CO2. And by cutting that, I have given away that potential sequestration. I might be having some advantages from solar panels, but I have given that natural advantages that I was getting from that forest. So even land use becomes a prominent thing. So these are some commonly used LCA matrices. And to give you a brief, We'll discuss these again in the future. Okay, so let's come to it. Like, you might be asking, what is it in for me? So what can the LCA do? Let's discuss this first. It would, in the first place, highlight the value chain efficiency. It will give you the chain of a product or a process. Something or similar you can see on the figure on the right hand side. You can see there is an extraction, like you have the cranes here. Then the construction phase, there's a building phase, then the recycling phase as the dumping phase. So you will become aware of the total supply chain of the process, where the raw material is coming from and where it is ending, and how much potential impacts that it might be causing. Again, it will give you an understanding of the product manufacture and the delivery stages, something that you might not have initially. Again, it will highlight the parts of the value chain that needs improvement. It might happen that there would be a small percentage or a small part of the process which would be causing the maximum amount of emissions or the majority of emission. And instead of just neglecting that process, it might make sense to just change that part of the process. And another part, it would highlight you the trade-offs. You can compare the different systems. You can compare different systems that would essentially deliver the same service or the same product. You can also benchmark the systems. You can say that this product is having this much amount of carbon. It will also give you the carbon footprint. You can say like this is the carbon footprint of this particular product, and it can also support your environmental claims. Now, suppose you say a paper bag is better than a polythene bag or maybe a jute bag. How do you support that? It's LCA. Could have a study where you certify, or it might happen in certain cases that a plastic bag is better than a paper bag. It just depends on the technologies and the actual system that you are like focusing upon. So this is what an LCA can do for you. Now, what can't an LCA do? It wouldn't measure your performance. It wouldn't give you any efficiency. It wouldn't give you the bricks and mortars or like the breakup of the capital equipment or anything like that. You would include the capital expenditure if you want, but it wouldn't give you that breakup. That is something you would do in a techno-economic analysis as you have studied in the earlier class. It wouldn't give you any compliance with the environmental. So this is something that you would have to determine. LCA won't do that for you. It wouldn't give you minor inputs. Like it wouldn't give you like every minor input or output that is there. It wouldn't be an analysis of your personal needs. It wouldn't be any information about your employee direct impacts or risk assessment. So these are things that the LCA won't give you. It wouldn't give you any minor data. It is only going to give you a bigger picture, and to assist you in doing a scenario analysis where you can construct different scenarios, as you saw in the case of the techno-economic analysis, and then compare them against the benchmark or the base case. So this is so I believe this understanding is clear what the LCA can do and what it can't do. Now let's again have a discussion on what are the different parts of the LCA. Now it can be divided into two things. One is phases and the other is stages. So by phases, I mean how the LCA is carried out, which is the like algorithm for the LCA. And by stages, I mean it's the product life cycle. So let's first see the stages. There would mainly be an extraction phase where you extract the raw material. Then there would be a manufacture phase where the manufacturing takes place. It could be a plant or anything. Then it would be the use phase where you use the fuel or that product. And finally, there would be a disposal phase. So these are the four phases which would be associated with any common product. And of course, in between them, there would be transportation. The raw material needs to be transported to the manufacturing site. The manufactured product needs to be transferred to the user site. And then the disposal site needs to be transported as well. These are common stages that any product would have. Now, once you have the flow sheet ready, you begin with the LCA, now which has different phases, which are four in number. The first one is goal and scope. You define the goal and scope of this study. This is what I'm trying to do, and this is what I'm not trying to do. You note it down specifically. You do an inventory analysis of raw material is going in, and how much amount of manufactured product is going in, how much manufactured product is going in, or how much fuel is going in the transportation sector. After use, what would be the leftover, what would be the mass and energy content of this. So you're preparing an inventory of all the mass and the energy balance. And this is again very similar to the things that you did in your techno-economic analysis. And this is also the reason why many a times techno-economic analysis and LCA go hand in hand. Of course, like both are different studies, you can do them individually. But if you are doing one, many of the data that you need, the initial data, would be same for both of them. Once you have the input and the output, energy and the mass balance, what you would do is impact analysis. What would be the impact of those input and output mass and energy balances? How much effect is going to cause in terms of the climate change? How much effect it is going to cause in terms of human health? How much effect it might cause in terms of ozone depletion? What could be an effect on the acidification potential, eutrophication potential, or my own life? And finally, the interpretation. You make an interpretation of this. If the result I'm getting correct, does that make sense? Or I'm making an error somewhere. And you would notice that all the errors are two-way. There is no single way transfer of data, which means the whole process is iterative. It doesn't mean that once you have defined a goal, it can't be changed. It can be changed. Once you have defined the inventories, it can be changed later on. And that's why like the whole process would be iterative. You start from one point, reach a set of solution, analyze it, and interpret the data. You find that here is a problem. You go back, make some adjustments, and analyze it again. And you keep on doing that iterative process till you are sure that this is giving me some meaningful results, which I can publish or which I can supply to the industry and government or the policymaker to make informed decisions. So let's come to certain principles of LCA. So it could be a guidance for product, process, and the constructed element selection. You could either focus on a product or a process or any of the elements that is a part of it. So, and the entire life cycle burden would be between different stages and process. You would be able to highlight this particular stage or this particular process is the place where I'm having a lot of savings, which might be acting as a carbon sequestrator, or these are the parts of the process which are causing a lot of emissions. Then it would be related to a functional unit. By functional unit, I mean like there would be a basis according to which all the calculations are being done. Suppose you have different types of bulbs or different technologies of bulbs. It could be the traditional incandescent bulbs. It could be the LED bulbs. Have the CF bulbs. How would you compare that? A functional unit for them could be maybe 1 million human hours of light. Human is the intensity of light, and by hours I mean the usage of light. So this is something I can use as a function unit, and I can compare these three bulbs on this particular basis. Or if I'm comparing the different modes of transportation, like a prospective function unit could be 10,000 passenger kilometers traveled. So it could be a total of 10,000, and it's a multiplication of passengers into kilometers. So it could be 4 passengers traveling over 2,500 kilometers, or it could be 100 passengers traveling over 100 kilometers. So in that sense, you can compare buses to cars. If you have a bus, maybe that can it's a hypothetical figure, like if it can carry 50 and it can travel over 200 kilometers, and you have a car with 4 persons, which is traveling over 2,500 kilometers, you have a same function unit, and then you can compare which one is causing more emissions. And only environmental considerations are addressed. Economic, social, and other aspects are considered using other tools. Economic, you have the TEA. For social, you have the social LCA, which is a topic for another class. We can take it sometime else. But LCA, in its traditional sense, wouldn't give you any social results. So it would mainly focus on the environmental consideration, the different emissions from different parts of the process, as well as the energy. And as I said, it's iterative. Each process or each part, each stage would use the results from the previous and the final stages. So you keep on doing it and arrive at the best results. As an example, a goal and scope can be updated regularly. Okay, so let's start with the initial parts. Now, I'm reiterating again, like these are the 4 stages of the LCA: the goal and scope, inventory analysis, impact assessment, and interpretation. And these all are based on the ISO standards. Understand all of these in one by one. Okay, so by goal, I make a statement that this is what I am trying to do. So in a good goal would state what is the intended use of the study, why I am doing this study, what is the audience, is it normal public, are the decision makers, is it a particular industry, is it the people of India that the study is aimed at, is it the people of the US, or is it the people of Delhi or people of Chennai? Because different LCAs could have different results. Like a study carried out in Chennai might not have so much of the interpretation or value of a person living in Delhi. No. And whether it is competitive, or should it be disclosed to public? Or is it a confidential report that you need to supply to an industry? Scope provides the mathematical choices. What is the methodology that you have chosen? It should include the functional unit, like I said, like passengers into kilometers traveled, system boundary, how you're doing the allocation, the impact categories that you're considering, the product system. Again, we are going to discuss them in detail. This is what the goal and scope is all about. So let me take you through an example. What would a goal look like? So if I read one particular goal statement, it reads like this. The goal was to generate a qualitative environmental profile of the management system for all the used oil generated in California, which means it's concentrated to the state of California. The results of the LCA, when combined with a closely integrated economic assessment performed by the economic contractor, will provide sufficiently broad information to be used by this particular industry, which is called Cal Recycle, to fulfill its duty pursuant to section so and so. Why are you carrying out this study? Intended use. Namely, provide suggestion to the legislature regarding possible policy changes to promote increasing collection and responsible management of used oil. This is the intended use. How this study could be used. What is the audience? The intended audience of the study is this particular industry, or all industries involved and affected by the management of used oil generated in California, and the public at large. But the focus is oil generated in California and public. The results of the study are intended to be used in comparative assertions intended to be disclosed to the public, which means it could be disclosed to the public. It's not a confidential report, and people can use it to compare. So this is what a good goal statement would look like. And it is expected that before you carry out an LCA, you write down a statement like this, which would be helpful in defining your methodology as well as your LCA as you move further. Now, next thing comes is the function unit, along with which all the values would be calculated. Now, a good function unit would be comprised of these 3 things: the quantity, quality, and the duration. If any of them makes a difference, it should be included in the function unit. So a good function unit should have all these 3 features. Take, for example, in case of generating light, 10,000 lumen hours. By lumen, I am giving both the quantity and the quality, and by hours, I'm giving the duration. And this gives me 10,000 lumen hours. Transportation of people, maybe 1,000 passengers per kilometer. Now, kilometer is giving me, 1,000 is giving me the quantity. Quality is given by my kilometer, and in terms of the people, and kilometer is basically giving me the sort of duration. Like if I know the speed, I can know the type. So, and this is giving me a good functional unit. So it must be clearly defined and measurable. You should be able to measure it and compare it. This is very important. It should have a unit. and it should be defined before you start collecting data, because unless you have it, it will become very difficult to collect what you don't know what kind of data you need to collect. You can always change it later, but it's always good to have that in mind before you begin. And there could be examples like generate light, transport people, and student housing. We'll discuss that. So let's compare like the examples. 20 million human hours could be a function unit. So if my function unit is this, for an incandescent lamp, I would need around 22 incandescent lamps, which would have a wattage of 60 watt, 9,000 lumens per lamp, and 1,000 lifetime hours. If I compare this with a CFL, it would have a much more bigger life and much smaller wattage. So if I have been comparing this on the on wattage, only the lumens or on hours, I wouldn't have got the right answer. But since my function unit comprises all the things in terms of million lumen hours, I can encompass both the wattage, the lumens, as well as the lifetime. And the third example could be an LED lamp, which would have even smaller wattage, smaller lumens, but much bigger lifetime. So this kind of function unit has to be used, which would take into account the quality, the quantity, and the duration. And the function unit for a light bulb could be maybe 1 million lumen hours. For a passenger bus could be 10,000 passenger kilometers, or maybe for a dormitory building, it could be 2,000 students in 1 year. 200 gives you the quantity, students gives you the quality, and 1 year gives you the duration. So this is how a good function unit can be chosen. Again, let's have another example. Suppose your goal is to compare the choice of bags. You have three choices. One is the plastic bag, the other is a paper bag, and the other is a cloth bag. Now there are three things. One is the weight or volume, and the amount, and the other thing is the times for which the bag can be used. Now, say for example, the plastic bag. It might be able to have 6 pounds of weight or 1 feet cube of volume, and it most of the time it would be used for one time. Compare that with a paper bag. It could have maybe 10 pounds of weight, 1 feet cube of volume. It's more sturdy. It can have much more weight, and it can be used 3 times. Compare that with a cloth bag. It could be used 50 times because there's nothing going to happen to it, and it could have much more weight to it. So a good function unit would try to encompass these two things: weight, or it could be related to the volume, and the times of the bag can be used, both the duration and the quality of product. So coming next, now system boundary. I believe you studied this concept in the techno-economic class as well. So a good system boundary would include the process stages that you want to compare. Now there are different types of system boundaries that you can take into account. Some of the examples are given in. It could be the gate-to-gate, cradle-to-gate, cradle-to-gate retailer, and cradle-to-grave. So what does they include? Say if I have the product stages where the raw material extraction is there, product manufacturing, distribution, use, and disposal. A gate-to-gate means the raw materials arrive at the gate, and you're just concerned at the finished product at the factory gate, nothing else. You're getting the raw materials at the gate, you're doing some manufacturing with them, and you're getting the end products. So that is the LCA from gate to gate. Then there is cradle to gate, which means you take care of the production of all the raw materials, whatever they may be. So that way, the cradle of all the raw materials till the gate of the finished product. Then there could be a cradle to gate with the retailer, where I also take into account the distribution and the retail sector, which is basically the transportation of the manufactured product till the user or till the retail shops. And there could be cradle to grave, which is the most encompassing one, which means I start with the production of all the raw materials till the disposal of all the raw materials. It's an end-to-end product. Now, you might be wondering, is it anything more to it? Yes, there is. There's a methodology called cradle to cradle, which makes or completes the whole cycle. Just a minute. So the next could be cradle to cradle, which means You start, sorry for this. You start with the grave and the products are recycled. And the methodology is called cradle to cradle. So you start with the end and end at the end. So the most encompassing are the cradle to cradle and cradle to grave. So these are the most reliable LCAs that you can rely on. If the study is gate to gate or cradle to gate, you should see the results with a pinch of salt, because there might be some emissions that are associated with the disposal of the product. So these are the different types of system boundaries that you can take into account. And this is what they mean. So I believe these are some common terms that you might be hearing in your daily life as well. Gate to gate, cradle to gate, and these terms are becoming common nowadays. And this is what they mean. And the system boundary, again, what are the important factors that I need to take into account these things? So if I'm assuming at a cradle to, if a system on that is taking care of the cradle, these are the things I will take into account. Material extraction. It could be extraction of crude, extraction of different material. It could be the farming products, like how I'm producing the different products, and different upstream processing, like refining of crude. It is an energy intensive process. So what would I use? I would use the equipment. How are they constructed? The iron and steel, those are going into equipment, needs to be taken care of. The fuel use. What is the kind of fuel that I'm using in my supply chain? Say if I am getting a cheap oil and that is produced in Venezuela, like it's a country that is known to produce cheap oil. And if I'm taking that, but that oil is consuming a lot of energy in its transportation, it might not make a carbon sense. Land use, how much land I'm using, water use, and the waste flows. Now, these waste could not be just the disposal phase, but the products that you are take for example, the mining operations as well as the drilling operations. It would have the waste associated with this as well. So we need to take into account. The second could be the manufacturing phase. You need to include transportation of parts, the assembly of parts, the facilities, the packaging, distribution, and the emissions from the facility. So the most common things that it will use would be the raw materials, the energy use, the chemical use, the equipment, and any co-products. Now, co-products would provide an interesting study or a complex study, which will again focus, but these are the things that you would focus in the manufacturing phase. Use phase. So in use phase, and going beyond the cradle to gate, there comes the use phase. How is the consumer using that product? Over what lifetime is the product being used? And it would depend on, say, I take the impacts of a typical lawn mower. It will depend on the frequency, how often I'm using it, the size of my lawn, the lifespan of the lawn mower, and the quality of the oils that I'm keeping or providing it with. So all these factors need to be taken into account. And we also need to take into account the uncertainty, like different people would use it in different ways. So we need to give a bigger picture to the final user, and we need to bring in the element of uncertainty and see if this particular process was to act in such a way, what would be the result on the on the total product. So again, how the product is being used, how the product typically is used, what variations are possible, and what ways the product could be damaged or it's leading to its failure to give the intended use. So these are some things that we need to take into account while we are defining the system boundary. The last thing would be disposal, recycling, or the reuse. So either we can dispose the product, either we can recycle the product, which means we disband all the raw material in it and use it from point zero, or we reuse it for some other purposes. So we need to take note of what we are doing, and all this would have different ways. So if we are, say, going for disposal, we are incinerating it. This would lead to a production or use of electricity, which would have its own emissions. If we are dumping it, you would have seen the sites that are common outside big cities. Like if you are living in big cities like Mumbai and Delhi, you could see huge mountains of garbage, and often you would see there's fire burning out of it. That is nothing but methane coming out of it. And as we are going to learn later on, each molecule of methane or each kg of methane is 25% more lethal than 1 kg of CO2. So if we are just dumping that product, it might the inorganic products. Say we are dumping vegetable waste or something like that. But if it's emitting methane later on, it would have a degrading effect on the environment. And this is what we need to take into account. So disposal, recycling, or reuse, this is again has a lot of sense, or like a lot of importance to how we do the LCA, or what are the values that we're getting in the LCA. And also we need to take into account many of the things would sometimes result in environmental benefits which are negative, say -5 kg of CO2 equivalent. So it doesn't actually mean that I have sequestrated that amount of CO2, but I have avoided. If this wasn't have been done, these 5 kgs of CO2 would have essentially ended up in the atmosphere. So that's why I am saying -5 kg CO2 equivalent. So again, the sign notation is important, how you deal with it. A minus sign doesn't necessarily mean that you sequestrated, you have like captured 5 kgs of CO2 from the atmosphere and brought in it. It also means that you have avoided these emissions which would have ended in the atmosphere. So with this, like these are the things that you need to keep into account as far as this system boundary is concerned. Then, okay, so there's one last thing which I forward, it's the transportation. You need transportation for extraction, for processing, to the customer, to the disposal facility, and you can't avoid it. Now, transportation is basically dependent on the fossil fuels. You do it either by trucks. If you do it by trucks, the fuel is diesel or petrol. Like most of the cases, it is diesel. And this diesel would have its own emissions. Not only diesel, these trucks would have some lubricating oils as well. Again, these are coming from fossil fuels. They end up to the emissions. These trucks are made up of maybe steel or iron. And the extraction of these elements would again have energy consumed. And these energy would be coming from fossil fuels. So you have emissions associated with them. So there are a lot of emissions associated, and that's why you need to define the system boundary really carefully. This is what I'm taking into account, and this is what I am not. So that the comparison becomes even more fruitful. You just can't compare apples to oranges. You would only compare the LCA studies which have a similar system boundary and a system functional unit. And that is why the concept of system boundary and the functional unit is very important. Okay, now coming to the phase 2 and phase 3 of the study. So before that, I would like to ask if anyone has any questions till this part of the class. Okay, I'm giving, so yeah, you can unmute yourself now.
As you said that, hello sir. As you already said that in big cities like metro cities like Mumbai, Delhi, there is a huge problem of disposal. Like we are garbaging and we are producing the CO2 as compared if we see. So what would be the other possibilities or other possible way?
Okay, so what is done in like the most developed countries is either you flare that methane, you capture that methane and just burn it. So by burning it, what you are doing is converting that methane into CO2. It's a simple reaction. CH4 reacting with oxygen, giving you carbon dioxide. In that way, the impact on the atmosphere is decreasing. But a better solution for that would be you use that methane for some energy purposes. You do anaerobic digestion for them, like something sort of biogas. You produce biogas, and that could be used for electricity production. So in many places in the world, you would see like biogas is being produced. Even there's a nice plant that has came up in Goa recently, like 2 years back. And what they are doing is they're producing huge amount of biogas and producing electricity. And it's at such a scale that they are not importing any electricity from outside, but exporting to the grid. So that plant has recently came up in Goa, and it might be worthwhile to study that if you are interested in this particular aspect.
Okay.
Anyone else? I can see one more hand. I don't know if this was the same.
Sir, could you please share any details about the Goa plant which is producing biogas from trees?
Okay, so the plant is an MBT plant. It's a mechanical biological treatment, and it's located in Salegaon. And the company, I believe, is something SGN or something like that. So that is the company that has constructed it. You just Google it and you will get enough information.
Okay. Thank you.
Okay. So we move further in case there are no future questions. So now coming to the second and the third phase of the LCA, which is life cycle inventory and life cycle impact assessment. So in a way, these are linked, but are taken at different stages. So this particular stage would essentially mean data collection. You collect as much data as possible from the different stages. So it could be either you do a physical survey, you go there yourself and do your own measurements, or you can rely upon certain secondary databases which maintain these databases and supply the information to others. And you can also consult certain papers, and you can also follow certain methodologies as were like reiterated by Professor Sonal in the previous session. In the life cycle impact assessment, you will be trying to make sense of that data, how that data fits in the bigger picture, and what are the potential impacts that are resulting if the data was to be correct. So let's try to understand that in more detail. Now, first, life cycle inventory. So there could be two types of data. One is the primary data, which would essentially mean that it is measured and calculated directly from the source. And you go directly to the plant or the process and make measurements using maybe a GC or using an emission meter or something like those. You measure the pollutants in the exhaust stream, maybe using gas chromatography. You read the electricity use. And the electricity footprint is something that you can get from the electricity power plant, or like if you have a coal-based power plant, you can like do some basic calculation and you can come up with these are the basic minimum emissions. Like a typical coal-based power plant would have an emission between 1,000 kgs of CO2 per kilowatt hour of electricity produced. So this is the minimum. So you can like make assumptions like this. And the other could be secondary data. Now there are different databases and literature available, and you consult them, and they're called secondary sources. And a few examples could be NREL, which is the National Renewable Energy Laboratories of the US. They have a huge database. And for India, I believe there are certain providers like GABI, or even Simampro has good amount of Indian data. So you can select that. And also you can have some proxy data in terms like I am producing like RDF. By RDF, I mean refusal derived fuel. So if I have a waste treatment facility and I'm producing RDF, and you don't want to go to the waste treatment facility and see what is energy content or what you're going, but you know that 700 grams of RDF could easily replace 1 kg of coal. So what you would do is the emissions associated with 1 kg of coal, you just multiply that with 0.7, and you can come up with the emission reduction or the emission potential of those RDFs. This is an example of the proxy data, where you are using proxy means to estimate the data. Again, this is a similar thing. The data sources could be primary data, which is direct measurement, or it could be secondary data, which means the LCI databases or journal articles. This GREET is basically for transportation fuels. It's a very extensive database that is made by PNNL, which is Pacific Northwest Laboratories, and it gives you a lot of data on the different fuels. So if anyone of you is doing a study on the different fuels, it might be electric vehicles or biofuels or crude, this is the place to go at. And the final is the proxy data or the estimated data. Impact assessment. You have all the data. You know where which all things are going in, but all things are going out. The next thing is impact assessment. How much impact those emissions are going to be. So with that, with impact assessment, let me walk you through an example. Say you have SO2 emissions. Now SO2 emissions would possibly, sorry for this, lead to acid rains. And these acid rains could lead to acidified lake, which means the pH of the lake has reduced. This would again cause to the death of the marine life, which could be mainly fishes. And finally, it could be a loss of biodiversity. So this is one particular emission that from different parts. The example could be chlorofluorocarbons. These chlorofluorocarbons, when emitted, would go and lead to tropospheric ozone depletion. By OD, I mean ozone depletion. These ozone depletion will lead to stratospheric ozone depletion. So these are the different layers of the atmosphere: troposphere, stratosphere, exosphere, mesosphere. I believe some of you might know it. And then once it is depleted, it would enable the UV radiations to enter the earth. It would cause diseases like human health and lead to diseases like cancer. So there are now two ways in which I can do the impact assessment. One is called midpoint and the other is endpoint. By midpoint, I am trying to ascertain how much acidified the lake would be for maybe 1 kg emission of SO2. If I'm releasing 1 kg of SO2 into the air, how is going to rise in a lake that is nearby? Or if I'm releasing 1 kg of CFC, how much ozone depletion it is going to lead it? Now, ozone depletion is nothing but the reaction of O3 with O2, giving 2 molecules of O2. So you can use simple stoichiometric and come up with a solution like this. So these are called midpoint indicators, but it makes much lesser sense to a common person like you and me. What I'm going to do, like if someone says me the pH of certain lake has reduced to 6 or 5, it doesn't make sense to me. But if I say the 50% of the fishes in this particular lake have died, it's quantifiable and understandable for me. Or if I say, if there is an ozone depletion, this would reduce my lifespan by 10 years. This is going to make an effect on me. It's much more understandable to me. But the relation or the calculation for these would be dependent on a lot of factors, which could be dependent on the location, the geography, your particular race, your like health background, and a lot of things. So there are a lot of correlations available. So there are two kinds of impacts that you can calculate. One is the midpoint and the end point. So if I do calculate the midpoint in the impacts, they have much more scientific evidence attached to it. I can easily quantify this much amount of SO2 is going to lead to this much acidification of the lake, or this much CFC emissions are going to lead to so much so ozone depletion. Much more quantifiable, much more scientific. But when I'm leading this to the end product, a lot of assumptions come into being, which might not be correct everywhere, but it makes much more sense to a common person or the policymaker. If I go to the policymakers saying the ozone depletion ozone layer has decreased by 10%, he might not be that much worried. But if I say the lifespan of a common person or the life expectancy has been reduced by 10 years, he is going to be really afraid, because 10 years is a huge amount, almost like 10% of your life has reduced. But the relationship between the midpoint and the endpoint would depend on a lot of factors, and it might have a lot of uncertainty at times. So these are the two types of impact assessments that are carried out, midpoint and endpoint. Both have their advantages and disadvantages. Now, coming out to another example, similar example, say CFCs, which are released to the atmosphere. Now, these CFCs are basically hydrochlorocarbons and halogens, and this is going to lead to midpoint indicators, and then this could have different damages. Cancer was one of them. It could also lead to crop damage or marine life or cataracts. And if I quantify a result, present my result in terms of this, it makes much more sense. But this relation between the midpoint and the endpoint could have much uncertainty in it. The research as it is carried out make these things better, but there is still a lot of scope. And it would again depend upon a lot on the history as well as the geography. So, so there are different kinds of life cycle impact assessment categories, and this is one of those, and it's called a recipe methodology that came up in 2008. And this is thought to be the most extensive one, which has 18 midpoint indicators and 3 endpoint indicators coming out to be a single one. So these are the endpoints which would be coming from the different emissions, which could be carbon dioxide, volatile solids, phosphorus, sulfur, NOx, CFC, or different fertilizers as DDT. It could cause different factors. As you can see, different arrows are leading to different things. Say for an example, like this CO2 would go to climate change, and this climate would cause change in infrared forcing, which is how much CO2 gets trapped, and it would damage the human health. Take for example another thing, which is this eutrophication. It would lead to algae growth, and this algae would damage the ecosystem. So different factors could lead to either one or more of them. And there are different methodologies available. Few one being like, it's called EDIP. I've shown you recipe model, and there is one of the most extensively used because it takes care of many midpoints, total 18 in number, and it also gives you 3 endpoints, which are basically human health. It's given in daily, which means disability adjusted life years, which means how much my life is going to reduce. Ecosystem services, how much is the life of species going to reduce in general, and what would be the cost of the resources. And you also have the capability of normalizing them into a single score, so that you have a single score that this process is giving me this score, and this particular process is giving me this score. So this is something very similar to the AHP that you have studied in the last class. Okay, so again, like how this classification is done. Now there are different emissions that could lead to a single impact. So it's very important to understand the difference. So let's take one impact category, which is climate change. Now climate change is the impact category. What is the result? It's the emission of the greenhouse gases. Now there will be different characterization models. For the climate change, the most common one is the IPCC. It's the Intergovernmental Panel for Climate Change. They have come up with a model. What is the indicator? It's the infrared radiative forcing, and it has a time factor which is 100 years time horizon. Now there are certain people who do it on a 25 years time horizon and a 500 time horizon as well, but the most common is 10 years. So with that, we have certain values which are given in the table below, which say that all the emissions which lead to climate change could be calculated in terms of CO2 equivalent, which means if I'm emitting 1 kg of CO2, it will be equivalent to 1 kg of CO2. If I'm emitting methane, it would be equivalent to 21 kgs of CO2. 1 molecule of CFC11 would be equivalent to 4,000 kgs of CO2. Similarly, 1 kg of sulfur hexafluoride could be equivalent to 23,900 equivalent of CO2. So all these chemicals, if released to the atmosphere, are going to cause climate change. And to quantify them, I am normalizing them to a single unit, which is equivalent to CO2. So what I need to do, I need to multiply the emissions by these factors, and this would give me the CO2 equivalent for that particular impact assessment category, which is climate change. Take for, okay, I have just one example here. So let's take, try to understand this with the help of an example. Say I have this process which is releasing all these gases. It is releasing 20 kgs of CO2 in total, 2 kgs of methane, 5 kgs of CFC11, 2 kgs of NO2, and 1 kg of sulfur dioxide. Now I know there are 2 gases in it, which is CO2 and CFC11, or CO2 and methane, that is going to cause climate change, which is global warming. Now there are again one gas which is CFC11, which would also cause climate change and stratospheric ozone depletion, because CFCs would cause climate change as well as ozone depletion. A chemical like NO2 would be responsible for both photochemical oxidation formation and acidification. A chemical like SO2 would only be causing acidification. So we have these 5 chemicals that are being released throughout the supply chain of a chemical. And what we are doing is we are trying to quantify what its effect is going to be like. So now this climate change is going to the global warming potential. This would go to ozone depletion potential. Photochemical oxidation formation would go to photochemical ozone creation. And finally, acidification would go to acidification potential. So I make a table like this. So I note down all the chemicals that are being released, which is CO2, methane, CFCs, NO2, and SO2, and the amounts in kgs. So the amount that are known to me. And here I note down the different characterization factor, which is, if I go for GWP 100, which means global warming potential over a lifespan of 100 years, and the unit is CO2 equivalent. So the characterization factor for CO2 would be 1. For methane, it would be 21. So every kg of methane released would have the impact equivalent to 21 kgs of CO2 being released. Then CFC 11, which would have an impact equivalent to 4,000 times. Coming to ozone depletion potential, there's only just one chemical that is doing it, and that is CFC 11, and that is the characterization molecule. So I just have one here. Coming to photochemical oxidation formation, it's in terms of kg of ethylene equivalent. I don't have ethylene being released here, but I have methane and NO2, which would lead to this particular impact. And the characterization factors is 0.006 and 0.028. And similarly, impacts could be written for acidification potential, for which the source is SO2, and I have SO2 being released, and I also have NO2, which would cause acidification potential. Now, if I have to calculate the global warming potential for this particular process, this is how I would do it. I would multiply 20 into 1, which is 20 kgs of CO2 multiplied by 1, that is the characterization factor, giving me 20 kgs of CO2 equivalent. Then 2 into 21, which is 2 kgs of methane into 21 kgs of its characterization factor, giving 42 kgs. And finally 0.005 into 4,000, because like the release might be small, but the characterization factor is 4,000 in here. That is equal to another 20 kgs of CO2 equivalent. I add them up, and the final CO2 equivalent that I get is 82 kgs equivalent. Note that the actual CO2 is only 20. I am also normalizing methane and the effect of CFC 11. That would have the same effect as the CO2, and the final CO2 equivalent that I'm getting is 82 kgs of CO2 equivalent. I could do a similar calculation for others as well, and this gives me the total results. 82 kg of CO2 equivalent for GWP 100. For the case of ozone depletion potential, I'm just multiplying 0.005 to 1, so it's 0.005. It's very less for ethylene, photo oxidation chemical potential, and a similar multiplication by the factors can also give me the acidification potential. The point to note down is that a release of 0.005 kgs of a chemical, which is CFC 11, which is 4 orders of magnitude smaller than CO2, could have a similar impact. Both are causing an impact of 20 kgs of CO2 equivalent. So it is both the quality and the quantity of the emission that needs to be taken into account. So let me take a break here again and let you know if you have any question with respect to this calculation, because this. Okay, so if there are no questions, let us proceed. So this is how you would quantify the different emissions and bring them under a single characterization value. And the fourth thing is interpretation, how you are going to interpret the results. Now it's a continuously ongoing process, which means the assessment is carried out continuously. And it's an iterative, as we saw in the earlier phase. Like you go see the results and then come up with the conclusions and recommendations. In case you find any problem, you go and redefine your golden scope. You include more inventories that are needed. You modify the data if that is needed, and you also include a lot of uncertainties. And go ahead. So now let's come to out what are the limitations of an LCA. Again, like this is something that we have done in the earlier slides as well. It's not a complete assessment of all the environmental issues. It includes a lot of them, but they are not all. There might be something that it can't, like there is no foolproof system. It tries to take in as much emissions into account as possible, but it's not a complete assessment. It cannot include every single process and capture every single input and output. That's just not humanly possible. You try to include as much as possible, but you just can't include every single process and like every single input and output. LCA data contains uncertainty, which means the rate at which electricity is being produced in India would be very different to it being produced in Australia or Brazil or US or Europe. You just can't take certain emissions. So if a process is good in India, it could be very different in the country of Australia, or in the country of Brazil, in the country of the US. So this is something that I tried to reiterate in the earlier lecture, which was production of ammonia from biomass. And that's why we need to have an uncertainty analysis as well. Supposedly, like tomorrow, maybe in the future, all my electricity is coming from solar. What is the effect is going to be? So I change the emissions associated with electricity and see the results. The characterization models are far from perfect. They are still in the game, like in the point of getting modified day by day. So that's why it makes much more sense to compare the different scenarios with the similar assumptions than to compare altogether different studies, because they could have been using different characterization models and which could have different assumptions, and it wouldn't make any sense you are comparing data on that basis. And again, like sensitivity and uncertainty analysis are also not fully developed. There are certain issues with uncertainty analysis as well. So with that, now let us come to LCA of energy systems. What are some things that we need to take into account when we are doing the LCA of energy systems? That is what the course is all about. Okay. So now this I have taken energy system which is based upon biomass, but it would be applicable to any energy system in common. So here are three columns or three colored, which is mostly covered by an LCA, less covered by LCA, and the least covered by the LCA. So most LCAs that you will find in literature will start from the biomass transportation, conversion, biomass distribution, and bioenergy use. This is what they're going to take into account. They are going to take the direct resources and the direct emissions. So this is what a normal study would take into account: biomass transport, biomass conversion, biomass distribution, and biomass energy. A few studies which are better would also go into the production of biomass feedstocks, which means it's going to take into account what amount of fertilizers have gone into it, what are the pesticides gone into it, what is the field mechanized that has been required. Say in the case of solar, how the panels have been produced, where the silica has been imported from, how are the diodes being formed. And very few will compare the impact of that on the land use change, which is also called the indirect impact. Now, suppose there was a land which already had a forest, or which was used for cultivating a food crop. Now I'm producing biofuels on that, or I have established a solar field on that or a wind field on that, producing electricity. Now that particular land, which was earlier being used for food or was used for sequestering carbon in terms of forest, is now being used, or it might be set up elsewhere. So it might cause problem with food demand or dietary trends, energy demand, like biomass production elsewhere, or like the trade policy, energy supply and cost. All these are called indirect resources. So the most extensive LCA that you can come across would also include these indirect resources. This is very rarely found, but people have reported as well. So this is the most common type of LCA that you're going to find. A few LCAs would also include the production of raw materials, and very few would include the changes of land use or the change that they inculcate in the system. And also these kinds of LCA have a specific name, which is called consequential LCAs. So with this, let me try to give you a brief about two kinds of LCAs that you're bound to come around. One is the attributional LCA and the other is consequential LCAs. By attributional LCA, I mean I have this system and I just want to see what the results are. Say I have a solar panel and I want to see what is the emissions per kilowatt hour of electricity produced. So that would be an attributional LCA. But if I want to see why I have one solar panel and I want to see what change it is creating, in the sense that if I'm using solar energy, I would render some of the coal-based power plants running at a lower capacity. Lower capacity means they are running at a lower efficiency. Lower efficiency means they would be emitting much more emissions that they would have normally emitted for the production of electricity. So that is where I am entering into consequential LCA, which means I am much more worried about the consequences of the introduction of a product into the market than the product itself. So the first kind of LCA would only capture or have a system boundary which just has the solar panels into account. We are not concerned about how the electricity was being produced and will be produced in the future. But a consequential LCA would take into account how the present intervention is going to cause a change in electricity production as well. It's called a status quo and this is change oriented. The data would be average data in this, but in this case, I would take the marginal data or the state of the art data, which is the best available. Again, like this is a static process, and this is effect that would be a lot depending upon the demand. It is much less sensitive to uncertainties, but it is very sensitive. So this is just for your knowledge, like these are two kinds of LCAs that are available. Most of the time you will come across attributional LCAs, but in case you come out with attribution consequential LCAs, you should know what the difference is. And it's not always correct to compare these two kinds of LCAs. So you need to compare attributional LCA with an attributional LCA and a consequential LCA with a consequential LCA. The reason being the data they have chosen is different and the assumptions they are choosing are also different. Again, we come back to this thing again, the land use change, which becomes a lot more important in the case of systems when you are dealing with like bioenergy or any energy system, because the land transformation is going to change the cultivation and of the crops, and the removal of biomass residues from the soil, which are a source of sequestrated CO2, and this might release more CO2, nitrogen oxide, and methane into the atmosphere. So it's again a very complex thing which you might want to study if you are going into this field of LCA of energy systems, and land use is a major part of it. Again, some people neglect this, but this is very important, is the water use. And again, like in the starting of this presentation, I gave you an example of like biofuels is the solution or worse than the, like, is it like the curse or the solution worse than the original solution? So that might be a reason, because if you see certain biofuels like soybean biodiesel or corn ethanol, they consume enormous amount of water. Compare that with petroleum extraction or oil refining, very less. So can we like afford to put so much of water in the production of fuels like biofuels? So it's again questionable. They might be nature friendly in terms of CO2 emissions, but have a look at the amount of water that they might be using. Does that make sense? Again, like this is not for us to answer. Our aim is to provide them the data, and it's up to the policymakers to make an informed choice. And this might be true for certain solar technologies like solar concentrators. They assume they consume a lot of water as well. Is it justified? Does it make sense? And this is the type of data that LCA would give us. Transportation. The transportation could be very different for like very different parts. Like here I've compared like 3 different parts which are like shipping pellets. So it could be shipping through ships and trains in different parts, and then so it has been giving the CO2 emissions, and it could vary differently for different crops and different places. There will be certain areas where the trains are highly used. There will be certain areas where ships would be used, and like so we need to take care of how the biomass or how the energy is being transported from one end to another, because that in itself would also have emissions associated with it. Now coming up with multiple products. So it would happen that a single process would end up giving you multiple products. As like is in the case of many renewable energy sources, the products could be twofold. So you have one single stream going in, and there are 2 kinds of products. Like take for example the biodiesel production process. It will give you biodiesel as well as the glycerin. So in case you have 2 products, how do you bifurcate the emissions between both of them? You just can't allocate all the emissions to one product. The emissions that are from the whole systems need to be divided into both the products. And how do you do that? Let's take an example for this. Suppose you have a unit process which is emitting 1 kg of CO2 maybe, and it has 2 products 20 kg of product A and 80 kg of product B. So if I do an allocation on the basis of mass, what I would do is I would divide this unit process into two processes. In one process, I am just having produced 20 kg of product A, and the emission associated is 20% of the total emission, which is 0.2 kgs. In the other calculation, what I would do is I would have allocated 80 kg of the product and 80% of the emissions. So I'm just doing it on mass basis. Total, I'm producing 100 kgs of both product and A, out of which 20 kgs product A and 80 kgs product B. So I allocate the emissions accordingly. 20%, which is 0.2 kg, go to product A, and 0.8 kg goes to product B. So this is one kind of allocation. The other could be based upon the economic value of these products, which could be, say, 20 kgs of product A is being produced, but it has a value of $900. And at the same time, the 80 kgs of product B that I'm having has an economic value of just $100. It might be produced in huge quantity, but the economic value is very low. The other allocation could be I allocate 90% of the emissions to product A and 10% of the emissions to product B, as can be seen here. I'm dividing the same process into two parts. I'm allocating 90 kgs of the emissions to product A and 1 kg of 0.1 kg of the emission, or 10% of the emission, to product B, because the economic value of the total production has like 90% is attributed to product A and 10% is attributed to product B, and the emissions change drastically. What was 0.2 in the first scenario becomes 0.9 in the second scenario, and what was 0.8 in the first scenario becomes 0.1 in the first scenario. So in real life, you are going to encounter this a lot, and you must make definite guidelines. How are you going to allocate emissions, whether it is going to be on mass basis or on the economic value. And the third thing is volume basis as well, which is almost similar. So this is how allocation is normally done, but it is very important how you allocate the products. Let me know if anyone has any doubts till this point, because after this we'll take maybe an example. Okay, great. So let's proceed further. Okay. One more aspect with respect to energy system, which might be taken more into account with respect to bioenergy system, is the biogenic carbon. Now, biomass can be a renewable source, a sustainable source of energy, only till we are growing biomass in place of the biomass that we have already cut or utilized. So if I take for a normal system or fossil fuel based system, the flow sheet is something similar to that I have on the right. I have the fossil fuel, and it goes to the fossil fuel system. I burn the fuel and the CO2 goes into the atmosphere, which keeps on increasing. Whereas in case of biomass, I use the biomass in a bioenergy system. I release some carbon into the atmosphere, and I extract that carbon back using growth of more biomass. But in this case also, when I'm using this bioenergy system, there would be some amount of energy that is coming from the fossil fuels. So it's not carbon neutral or carbon intensity is zero. It has some intensity to it, because this fossil fuel and this geologic carbon that is going into the atmosphere is not sequestered back. It's only the biogenic carbon that is getting in. So when we are dealing with fossil fuels such as biofuels, which have a conversion or retake of CO2 back into the growth phase, we need to be very careful when dealing with the biogenic carbon and the geological carbon. The geologic carbon would cause a CO2 emission, whereas a biogenic carbon wouldn't. A biogenic carbon is very similar to burning of biomass. You just burn the biomass, and the only thing that gets is the CO2, and CO2 would be taken back when you grow new biomass. So this is the biogenic cycle. But in case you're going for a bioenergy system, there would be also intakes from the solar energy. So in that sense, no energy system has a zero emission. All of them would have certain emissions till the point our supply chains are not fossil fuel based. In the future, when we are a lot more dependent on renewable energy. We can say that our energy systems are maybe carbon neutral or carbon negative. But as of now, no matter which technology you choose, be it the solar, wind, thermal, hydro, all have emissions. It might be less or large for someone, but all of have some emissions associated with them. Okay, so now let's take the same example for the ammonia production from biomass. I would skip this slide because we have already explained the process. It's the production of ammonia from biomass and through the gasification process. And we have chosen 3 different case studies, which was bagasse in Brazil, straw in India, and eucalyptus in Australia. And this is what the flow sheet looked like. We have the biomass production phase, we have the gasification, we have the gas conditioning, and finally the ammonia production. This is what the LCA would give me. It would give me the which kind of emission are coming from which phase of the product. Like say in the growth of biomass, the emissions are negative, which means I am taking in CO2 from the atmosphere, and that is what is happening. I transport the biomass. There's some diesel consumed. I release it into air. I have the gasification process. I release again some CO2 into the atmosphere. I have the methane reforming, which would consume some fuel. I have some emissions. For compressing, I need electricity, which would come from the grid. I have some emissions associated with electricity. The PSA would mainly release all the CO2 and give here hydrogen. So all the CO2 is now going out. So the LCA would be the sources and sinks of, in this case, I've shown you what are the major sources and the sinks of CO2 in this particular process. Okay, now let's try to compare the 3 flow sheets again. Say global warming potential. It could be very different for the 3 different feedstocks in 3 different countries. Like take the case of India. The electricity for grid, this is the global warming potential of kg of CO2 equivalent per kg of ammonia produced. And we have the 3 different cases on the x-axis and the straw cases for India. For Indian case, we have dirty electricity, which is based on coal. So that's why even if the electricity in terms of kilowatt hour is the same in all the 3 cases, the emissions associated is very high in India, second for Australia, and very less for Brazil. Like it's the highest for India, then a bit lesser for Australia, and the least for Brazil. The reason in India, the electricity production process is very inefficient, and we are based on coal. In Australia, again, it's based on coal, but the processes are much more efficient. In Brazil, where the bagasse is being used, the electricity is much more of hydro-based. So that's why emissions are very less. So same consumption could have different emissions in parts in different parts of the world and lead to different results, even if the flow sheet is same. Take for the example of ozone depletion potential for the same production of ammonia. And here it is like kgs of CFC equivalent per kg of ammonia produced. If I take the case of, again, India, the maximum emissions are coming from transportation as well as electricity. In case of Australia, there are hardly any emissions from electricity because the processes are very efficient and even transportation is efficient. Now take the example of Brazil. It has a lot of emission associated with reformer fuel, which is absent in Australia. It is somewhat similar in India and Australia. So again, like the same potential could come from very different sources for the same process. Take the case of eutrophication potential, freshwater eutrophication. Now this is a conventional process where the ammonia is produced from natural gas, which is a fossil fuel. If I am producing ammonia from biomass in India, I would have a eutrophication potential that is almost double than what I would do from natural gas. So in essence, I might be saving some in terms of carbon dioxide, but that's not all. If I'm taking into account eutrophication, which means the amount of nutrients that are going into the water bodies. So what is going to happen? I will just give you an example. In India, I'm using a lot of fertilizers as well as pesticides, which are attributed to both the products in terms of the straw that is produced and the rice that is produced. And now this fertilizers and pesticides end up into the water bodies, increase the water content, increase the nutrient content in these water bodies. With the increased nutrient content, a lot of algae grows in these water bodies. You would have seen in the ponds in the villages, it's always covered with green skime or algae. These algae would block the way of the sun and the sunlight from reaching inside the water bodies. It would kill a lot of marine aquatic system, and that's what is called eutrophication. So in India, if I'm using a biomass-based process, the eutrophication is going to be really high. It's almost double than the fossil fuel resources. The same goes for marine eutrophication. That's for India. The third term is agriculture land application. Now we had three different fuels, which was wood, straw, and bagasse. Now straw and bagasse would only take the area of the fields. But if I consider wood, which is grown in Australia, it has a lot of potential because I would be emptying a lot of land, which already might have some agriculture facility going on it. And that's why the wood potential or the potential for agriculture land application is very high in Australia, where I would be specifically growing energy crops for production of ammonia. If I'm consuming the case of straw or bagasse, these are side products. These are not the main products. Whereas wood would be specifically grown for the production of ammonia. And that's why it would have a huge land application as compared to natural gas, to ammonia product, to ammonia process, which is a conventional process. So these are some of the results that the LCA system would give us. Again, like I can normalize all of them to a single unit. So if I normalize them, of course, we are better in terms of the natural gas to ammonia process. But if we look at individually, there will be certain impact factors where we are already on a higher than a fossil fuel based process. And then we would go for a multi-objective optimization like this. So with that, I had another example to discuss, but let me leave that. And I would like to give you some experience with the type of software that are being used for LCA. So let me share my screen and maybe in a couple of minutes take you through SEMA Pro, which is one such software. This should be it. So I believe everyone is able to see my screen. So this is one particular type of software that might be used for calculating the life cycle assessment of different processes and products, and specifically renewable energy sources. We have an interface which looks similar to this. And
sorry to interrupt you. We are not able to see the screen, sir, right now.
Okay, let me share it again. Is it visible now? Maybe anyone can answer.
No, sir.
No, sir.
Okay. So what I will do is I'll share my whole screen, and that should be able to do it. Okay. I believe now it should be visible.
Yes, sir.
Yes.
Now visible.
Okay. Okay, great. So this is one particular type of software. So I don't have time to teach you like how the software works and all those things, but maybe I can give you like certain solutions that it already have. So it has a lot of databases for different places, and it would have the material streams. To give you an example like this: agricultural, ceramics, chemical, food, fuels, and whatever you would need. And it would also have energy streams. Now let's take an example by fuel. And say I am producing energy from photovoltaics, and I go to market and infrastructure, and I can estimate what would be the emissions associated with the construction of this fuel. So maybe I'll go through it. So I'm going for this particular database, which is photovoltaic facade installation. 3 kilowatt peak is the capacity or the rated power. It is based upon the multi-silicon, laminated and integrated technology, and the profile is global. you can see that in different ways it would be written where they're applicable. The GLO means global, and then there would be certain other terms. Not in this. Okay, let me show you this first, and then we will go. So we have a lot of databases, and you can read a lot of documentation here, which gives you the goal and scope, something similar that we have discussed. See, this is like when the study was done, and then when it was applicable, maybe like it was done in 2011, and the results can be found to be true till 2018, and it will give you the different inputs and outputs. And the best thing that you can get is this is the same methodology, the recipe methodology that we chose, and it can help you create where the emissions are coming from.
Excuse me, sir.
Yes.
So this software is open source software?
No, this is not open source. This is not open source. So there are certain open source software like OpenLCA, which you can find, but the cost is not basically of the software, but of the databases. So it's the EcoInvent databases that I'm trying to show you that are a bit costly, but there are a lot of free databases that are available. And I would suggest if someone is interested, go to OpenLCA. It's a really easy software to understand, and it also has many databases which are freely available. So it could be a great learning experience if you use tools like OpenLCA. And also like LCA, if you see, the methodology is not very difficult. You can do everything in a simple Excel sheet. So if you just Google like Excel formats for LCA, you would also find many. I wanted to take an hands-on on this, but like we had a limitation of 14 sessions, so that couldn't happen in this particular FDP, maybe in the future. But this thing is another interesting thing. How would you do an LCA? So it could be either on softwares, like good open source software would be OpenLCA, and even you could use your own Excel sheets and derive your own like calculations. You'll end up getting the same results. It's not that difficult at all.
Okay, thank you very much, sir.
Okay, so this okay, so it's very small. So let me try to increase the size. How do I do that? Yeah, this should be able to do it. So software like this creates a whole supply chain. Say if I was to produce one piece of this 3 kilowatt peak solar panel, this is the amount of CO2 emissions, which is 6.19 10 to the power 3 kgs of CO2 equivalent. So these are the types of CO2 equivalents that I would be emitting into atmosphere if I were to produce this. And it also gives me a whole supply chain where the emissions are coming from. And I can do not only the global warming, but also the different characterization factors. It could be like, say I chose the ozone formation. So it can do that as well. Sorry?
Sir, which result you are showing? In this 6.19 into 10 to the power 3 CO2 emission for 3 kilowatt PV production. So
Yeah.
all CO2, all emission is included from the raw mining from silicon
Yes.
to the whole conversion from
Yes. That's the beauty of this software or the LCA. So you would need, so if I expand this, it will go into like, so this is the NOx emission that have come here. And if I increase the percentage, or like I decrease the percentage, it will become much more complex. So you can see the aluminum is getting extracted here. You have the electricity going in. You would have the silicon extraction, the silicon casting here being taken into account. And you would also have the blasting, the blast furnace for copper that is being taken into account. So I believe it answers your question. So similar answers can be derived for different sources of energy, which could be renewable or non-renewable, and you can make your own life cycle assessments. So this is just to give you a visual experience of what the things look like. With this, maybe I will stop here, and I would be happy to answer any other questions that you might have. Or in case you have some other questions regarding the software, we can also have a discussion on that.
Thank you so much, Dr. Pratham, for this very interesting session on life cycle assessment.
Yes. Thank you, Professor Pratham.
So for the participants, thank you so much for being with us for this 5 days. And with this session, now all the sessions for the course which involved any teaching or learning, those are coming to an end. And only one last session remains, which is basically the feedback and the evaluation test. So as you have been observing, I mean, we always have the last session from 2:30 p.m. onwards, but we have received a few requests from some of the participants to have it somewhat later due to some engagements on their end. So we are proposing 3:30 p.m. And a 2-hour duration, 3:30 to 5:30. We will be sharing a Google form, 2 Google forms, one for the feedback, another for the question answer evaluation test. So please let me know. I hope everyone is available for that slot, 3:30 to 5:30.
It's better to keep on a 2:30, sir.
Sorry.
Some of the engagements we
Sir,
are having,
yeah,
because
yeah.
the official hours up
Correct,
to
sir.
5 o'clock. Sir. We can't
Correct,
manage
sir.
after
As
5.
per your schedule, we have scheduled things. So
Yes,
5:30
Okay.
will be little problem. 2:30, 4:30 is okay, sir.
2:30
Yeah.
to 4:30 is okay?
Yeah,
For
yeah.
everyone?
Yes.
Whatever schedule is, it is okay.
Okay, great. Okay then. So 2:30 to 4:30 seems good for everyone. So then we will float it at 2:30 only, and we will finish it up by 4:30.
Okay, sir.
Hello.
Thank you.
Hello.
Yes. Yes, madam.
Hello.
Yes.
Actually, what is the time limit of submission of the test and feedback? I mean,
Anytime
can we
between those
submit it
2 hours.
anytime? I mean, within 4:30?
Yeah. Anytime within those 2 hours, we will float the question paper at 2:30, and you will have 2 hours time. Yeah. Are you able to hear me? So you can submit.
Yes.
Yeah, you can submit it anytime before 4:30. So all the submissions till 4:30 will be acceptable, and after 4:30, I mean, we'll keep a cutoff because it has to be some cutoff. So after 4:30, we'll not accept any submissions, only till 4:30. Okay. So
Thank you.
yeah.
And sir, please share the recordings of. Can you share the recordings of all the sessions?
Recordings will share. Yeah, actually we were in the process of that, but because of so many things going on, we couldn't do it so far, but we will do that for sure.
Okay.
So we will upload it in a Google Drive, and that will share the link for the Google Drive. And the PPTs for these last 2 sessions also we'll just share right away within next half an hour. And so 2:30 we will be floating these 2 forms. One will be the Google form for feedback, another will be for the question paper. Please make sure to fill both the forms, and that is mandatory from AICTE side, so that their certificates can be processed. So please fill both the feedback and the question paper forms.
Sir, good afternoon, sir.
Yeah. Yes, sir. Please go ahead.
So Google.
Sir, this is Dr. Adhikari. Sir, we
Yes,
had
sir.
network issues every day. I hope you know. So, please consider us those who have got in, got out, got in, got out. So please don't mark us absent, sir.
No, not at all. So we understand there will be issues at your end, and that's why we are taking into consideration even if there are logouts or logins, relogins. So that will be taken.
Thank you, sir. Thank you, sir.
Yeah.
Thank you.
Sure.
Sir, good afternoon, sir. This is Nagarjun Reddy, sir.
Yes, sir. Please.
Sir, shall we log into this Microsoft Teams, or are you going to forward mail ID to our mail ID, sir? Feedback
We'll
form
forward mail IDs on the same email IDs on which you have been receiving all communication. We will send the link for the Google Forms on that same email ID. Just make sure to submit it before 4:30.
Okay, sir. Thank you, sir.
Good afternoon, sir. Sir, I have a query, sir.
Yes, sir.
Sir, actually, you will be sharing the feedback and question through chat box or through mail, sir?
Through mail, through email.
Okay, so sir. Because now, sir, yes, sir. Because sir, here my chat box is not enabled actually, so that's why.
No problem. We will not use Microsoft Teams for any feedback or question paper purpose. It will be through email for sure.
Okay, sir. That will be good, sir. Thank you, sir.
Yeah. Most welcome. So, one thing I would like to request all the participants, if you can put on your cameras, we can take a snapshot, a screenshot of this thing for also as a record, and or for also AICT also wants that. So please, if you can put on your cameras for a while, we can take a screenshot of this thing at our end. I see only few people. Can you please, if others also, please, you can put on at least few people more. Few more people we need.
Good afternoon, everybody.
Thank you so much, everyone.
Thank you.
Yeah. So thank you so much. It was really nice being with all of you, and it was really very interactive sessions, and we really enjoyed interacting with everyone. And we hope to see you in the campus once the COVID thing is over. We'll probably organize more programs, and we hope to have physical presence and have physical interaction with everyone. Once
Thank you, sir.
Yes, sir. The way you organized the program, it is awesome. It was very nice, and you are so humble, so polite, and so helpful. Any doubts, any queries, you are always there. So nice of you, sir. Sir, you will be providing those links on 2:30, right?
Right. 2:30 we will be emailing you, all of you. Yeah.
Okay. And sir, and for
Sorry, we are losing your voice in between.
half an hour or what?
It will be 2 hours for filling up both the forms. So one feedback form, another question answer. 2 hours will get. By 4:30, please submit both of those.
Okay.
We all the participants, I thank Professor. You are giving a lot of information this program. Really, we are happy. It is such a wonderful. You are conducting very nice manner. Your time and schedule, everything is perfect. Really, we are enjoyed, Professor. Really, thank you. Thank you your coordination and organizing such a wonderful program, Professor. Thank you, Professor.
Thank you so much.
So thank you, sir. It's a wonderful event. Thank you once again.
Thank you. And I would also like this moment to just acknowledge my team members. Actually, I'm not the only one. So Professor Pratham and me, both of us are the organizers, and he has been also equally involved with this. Though he is a very, humble person, so he puts me in front to speak. So you feel that I am doing the things, but he is also equally involved. And also there is my PhD student, Priya Gupta. She has also been very actively involved and doing a lot of things. So it has been the team of 3 of us who have been managing the coordination of the program, actually.
Yes, really good, Professor.
Very good program, sir. Yeah, we must admit it's a very good program. And so, lastly,
it's a hassle-free also.
Yeah. You people made it hassle-free.
Yeah, due to Microsoft Teams, there have been some hassles somehow.
So lastly,
despite our best attempts. So we'll try to see.
So
maybe next time we can have some other platform if we have online courses, because there are some issues with Microsoft Teams. We discovered those. Yeah.
Yes, Google Meet was a little bit better, I guess.
Right.
Yeah, Google Meet is better. So lastly, the attendance will be uploaded by 2:30, or it will be later on? You will be
Attendance is actually, it's taking a lot of time to process. What is happening that for each session we are getting a log of like 400, 500 logins and logouts. Because repeatedly
Yes,
people are connection coming back. So processing that is taking a lot of time, and it has to be done manually because
so
we
that's why
cannot really.
we are a little bit.
So hopefully we'll do it
That's why
by today, and we will share with all of you hopefully by tomorrow, let's say, because it is taking time on our end. We were trying earlier also, but it is taking some time.
Okay,
Yes.
But rest assured, we will take into account all the logins and logouts. Those will be accounted for, and those who have been around, they will be definitely getting attendance. But for your confirmation, we can share it by tomorrow. Actually, to be difficult for us.
It is difficult. Okay.
Thank you, sir.
Thank you, sir. Thank you.
And thank you, sir, for your sharing the slides.
Thank you, sir.
All these things, it's very very thankful for that.
Okay.
Okay. Thank you. Thank you so much.
Thank you.
And the study materials are very apt. I have gone through almost all the study materials. They're very apt and very much, to the point. Thank you again. Thank you again for preparing those beautiful slides, which we can also share to our students. It is very much helpful.
Thank
really.
you. Thank you so much.
Thank you, sir.
Thank you,
Okay.
sir.
Thank you, everyone. So
Thank you,
then
sir.
we'll end the session
So
here.
may I leave? May I leave, sir?
Yeah, sure. We'll be ending the session here, and hope
we'll be
to
back
have
on 2:30.
Yes. Any further correspondence if you have, you can do through email, and we will be always available on email. So we will end the meeting here. Okay.
Okay.
Thank you.
Okay, sir. Thank you, sir.
Thank you,
Thank you so
Pratham.
much for this.
Thank you. Thank you so much.
Yeah.